we have a new paper in town, which is Transformers², and it is for self-adaptive LLMs. And it comes from Sakana AI. So if we visit their website, sakana.ai, all we have got is they are building world-class AI research lab in Tokyo, and they are democratizing AI in Japan. And that is how much is there on the website. And if we visit the blog post, they have given an image of an octopus, and they have shared a tweet which says that the octopus has the ability to change its color and adapt to the environment that it is in. And that's how they wish the LLM model to be, just to adapt itself to the different prompt that is given as input, and so the image of an octopus on the blog. So they are proposing a machine learning system that dynamically adjusts its weight for various tasks. And so they've named Transformer², which is a two-step process. So basically the idea is that you have the user query, which comes in as the first pass, and the model understands that it's a math question. During the second pass, the model gets updated, and the answer that comes out of the model is that of the answer to the math question. So the model has dynamically updated its weights, which is this block, and hence the color changes from black to red in this animation. And the model gives the output in the second pass that is specific to the scenario in this case, which is the math question. So what are self-adaptive LLMs? It can be a group of LLMs, or it could be a standalone LLM that can evaluate and modify its behavior in response to change in the operating environment. So if the environment changes, the LLM should also be able to modify itself or its behavior, which is just changing its weights in order to give a different output. Then we can say that it's a self-adaptive LLM, and it should happen without any external intervention. So it could be that, whenever we get a query, we will have multiple LLMs, each specializing in one task. Let's say this is a specialist in mathematics, this is a specialist in reasoning, and this LLM is a specialist in language. And the system dynamically routes the query to the specialist one. And at the output, we get the response from the specialist one. And this is more of an ensemble system, if you like. So in a machine learning system, you can have multiple models that are working together in order to produce the best accuracy or any best metric possible. This is one way that we can achieve it. The next way we can think of is that, we have multiple modules inside a single LLM. And whenever the query comes, the module that is a specialist in the nature of the query gives the response. And each module will be a specialist in this case. For example, module 1 could be a specialist in mathematics, module 2 could be reasoning, and module 3 could be language. And the response that we get depends on the query that we are receiving. A good example for this one could be mixture of experts. But in case of mixture of experts, the query is dynamically routed to the module based on each token that it gets in the query. But in case of the self-adaptive LLM that has been proposed, it goes based on a single sample. For example, if you ask a question, what is the weather like today? The entire sample is considered before the LLM actually decides which module to use and then gives the response. So like I said, they're saying that Transformers² employs a sample level module selection strategy versus the mixture of experts, which usually uses a token level strategy in order to choose which module to use. And they're saying that they're using singular value decomposition for LLM fine-tuning. So this is one of the contributions or novelties of the paper as well. So let's look into singular value decomposition. So we all know that neural networks are composed of weights, which are nothing but matrices. So in this example, let's say it's a matrix W. This matrix can be decomposed into three matrices, which is U, V, and the diagonal matrix. So the idea is that once W is factorized into these matrices, they can be multiplied in order to arrive back at the weight matrix. Now the thing is, this is a diagonal matrix with values just in the diagonal, and we don't have any values outside of the diagonal. And this is usually in descending order. We can probably throw away some of these weights, and we arrive at an approximation of this, which will be W dash instead of W. So whenever we are given an input X, we can have fine-grained control over what we are getting at the output. For example, let's say we have a column here and a column here. Let this be the first column. And let this be the first column in this matrix, and it gets multiplied with this first singular value, which is here. So by just controlling or by just modifying this value, we have fine-grained control over what the output that we are getting here in the weight matrix, which is W dash. So this diagonal matrix, or more specifically, this vector in the diagonal, can easily orchestrate the value that goes into this matrix. And this is the beauty of this idea. So what we are saying is that we actually have to train in order to modify just this diagonal value, and we don't care about training the entire weights W. And that is where SVD kind of simplifies the computation that's needed in order to train the model. So more specifically, we can say that, for the output for a sample yi is the product of the singular value sigma I with that of ui and vi on the input x. So using the idea of singular value decomposition, they are proposing singular value fine-tuning. So how do we go about that? They're saying that singular value fine-tuning learns simple vector z that provides targeted modifications to each singular value component of w, independently yielding new weight w dash. So it comes with several benefits basically that they have listed here. So let's go over one by one, but let's understand how they train this model first. Basically, as we can see, this is the transformer block, and it is formed of the weights, which are M matrices. If we take one matrix, we can decompose it into U and the diagonal matrix sigma and the V matrix. So if we multiply them, we arrive back at the weight matrix that goes in here. So what they're doing is they are freezing these parameters, which is U, sigma, and VT, and they're just modifying the parameter Z, which goes as the diagonal multiplication matrix along with those. And using reinforcement learning, we are just training the parameters of this matrix, which is a diagonal matrix, or in other words, we're just training the values of this vector that goes in the diagonal, and we don't modify any of the weights of u or sigma or v of t. And during inference, they are using three techniques in order to swap the z matrix that goes in here, basically. So the three techniques that they're using is prompt-based adaptation, job classifier-based adaptation, and mixture-based adaptation. So let's look into each of those when we look into inference. So parameterizing this way seems to have some benefits, and they have listed three of the benefits, which is that of negligible parameters. Given that we are just dealing with vector z and not big matrices, we now have very less parameters, and that's a big advantage. And LoRA also has less parameters, but the thing they have pointed out is that the ability to affect the weight matrix in a full rank manner technically provides more information than low rank approaches. So basically, because we are reducing the rank in case of LoRA, the amount of impact that we have in the weight matrix seems to be less. With SVD, because we are dealing in a full rank manner, it seems to provides more information than that of the LoRA approach. Next one is high compositionality, which is that, we can do all sorts of algebraic manipulation, such as, composing A plus B and all that, and interpolation between different trained models, which is not possible when it comes to LoRA as well. And the next one is regularization. The approach that we have taken seems to be an effective form of regularization, and this seems to enable us to fine-tune for arbitrary downstream tasks with only hundreds of data points without the risk of collapsing or overfitting. So if we have a very less number of data points for fine-tuning, then again, this approach seems to be better than that of LoRA. Somewhere when we were talking about training, they said that they were using reinforcement learning algorithm. Here they have given the details. They're saying that they are using the well-established seminal reinforce algorithm, which dates back to 1992. And they are labeling each of the generated answer y for correctness, which is a value between -1 and 1. They also regularize the reinforce algorithm using a KL penalty, basically KL divergence, and they're just obviously adding a regularization term to the standard optimization term. So after the training, we'll end up with K set of vectors. Let's say we have 3 vectors corresponding to maths, reasoning, and language. And during inference, we'll have to use these vectors in order to do the inference. So how does the LLM choose which vector to go for? Like we said before, it does a two-pass inference, meaning in the first pass, it's going to decide which of these it's going to use. It uses 3 techniques in order to decide which of these vectors to go for. So we'll look into those techniques. But once it is decided, let's say the prompt is about Max and it decides to use this one. And in the second pass, it uses this vector, ignoring these 2, and gives the output just using this vector. But let's see what are the 3 techniques that it uses. So the first technique that it uses seems to be that of prompt engineering. The prompt that they're using for making the decision in the first pass, they are calling it as the adaptation prompt, and it looks like this. They're saying that analyze the given question and classify it into one of the 4 categories, be it code or math or reasoning and others. And for the code, they're saying questions asking for programming solutions. And the instruction is consider the primary focus, skill, and knowledge required to answer the question. And at the output, format the response as follows. And all that the LLM has to do is give a category. So once it gives the category, and then at stage 2, we can use that category to decide which vector. Next comes a classification expert. So you might have guessed by now, we will have a separate head that is going to decide between the expert XZC that are learned in the same fashion using a small set of data set that's collected. So that data set is used in order to classify which of the K tasks that the fine-tuning is going to involve. And we will use that same classification head, if you like, in order to decide which of the task the input prompt is, and we will use the vector accordingly. So the third approach is that of few-shot adaptation, where we can have, a separate vector that is, let's say ZK, that is a weighted sum of these vectors. And at inference, this vector can be actually learned using a few-shot scenario. Based on the input prompt that we get, we then decide what's the weight for the vector that we use. We'll directly use this one based on the input prompt that we get. So that's what they are mentioning here in the few-shot adaptation. Because the LLM has the ability to learn about something it has not seen during training using few-shot prompting, we can use that advantage of LLM in this case. And we can say that for each of the optimized weight matrix, we'll be producing an entirely new Z' vector by interpolating between the K learning task that is weighted by the coefficient alpha K. So basically, this Z' is a weighted sum of the different ZK that we have trained. And we'll be using this one based on the prompt that we are getting, or we'll be searching for this value based on the prompt that we are getting during inference. So that's pretty much the idea of the paper. They then move on to the experiments, and under the experiments, they show results comparing with Llama 3 8 billion instruct model and the Mistral 7 billion instruct v0.3. And they also show results for Llama 3 70 billion instruct. For all the 3 models, they compare the LoRA with SVD fine-tuning, and they say that the performance is better when it comes to SVD. And they also go ahead and show the results for vision language models, and they show that in the case of VLM, SVD Transformers² is better than the LoRA. So with that, I'm signing off, guys. Thanks for your attention in this video, and I look forward to meeting you guys in yet another video. Until then, take care.